Sir, good afternoon, sir. Migilan, sir.
Good afternoon, sir. Nice to meet you.
Thank you. Feeling the same. PPT share பண்ண test பண்ணிட்டு please.
Yeah, 1 second. I hope my presentation is visible, sir.
Yes, sir. Yes, sir. Of course.
Sir, no need to call me every time as sir, since I'm your old student. You can.
In the public platform.
Yes, sir.
I must obey me.
Okay.
Thank you.
సర్లే చూస్తాంలే కానీ రానియండి.
Sir, Chief Guest, sir.
Yes, sir, I'm audible.
Yes, sir. So shall we start, sir? Since we crashed under participants, sir.
Yes, sir, we can.
Yes, sir. Sir, should I start? So, good afternoon, everyone. Gathering this 6 days International Faculty Development Program on futuristic research in mechanical engineering. Today is the third day. I'm very happy to welcome you all on behalf of SRM University Ramapur, Department of Mechanical. Our respected Chairman, sir, Co-Chairman, sir, our beloved Chief Director, Director, sir, and our Honorable Dean ENT, Dr. Murali sir, and our beloved Vice Principal Academics, Dr. G. Prabhakaran, as well the head of the department, sir, and other heads of the departments and faculty members. As well, I am welcoming each one of the participants in this faculty development program, those who are attending regularly. And finally, I want to welcome today's chief guest, Dr. Mugilan Narayana Swami, sir.
Thank you, sir.
Yes, sir. And right now, I request one of the coordinator, Mr. Ganesh, please introduce about our chief guest. Ganesh, sir.
Yes, sir. Yes, sir. Yes, sir.
Yes.
Thank you, sir. Dr. Tanigalan, sir.
Yes, please.
It's my pleasure to introduce today's chief guest, Dr. Mugilan Narayana Swami, sir. Sir is a postdoctoral researcher, energy scientist, School of Advanced Material Science and Engineering, Shankwang University, South Korea. Sir has done his master degree in nanoscience and technology, Pondicherry University, India. Sir has completed his PhD in School of Material Science and Engineering, Tsinghua University of Science and Technology, China. Also, sir has published more than 10 research papers in the reputed journals. He have received many awards continuously. Recently, he have received a first prize award in 10th China University students national level polymer material innovation and entrepreneurship competition. Sir, Dr. Mughal sir, you can continue, sir.
Yes. Yeah. Good afternoon to one and all present over here. Myself, Dr. Mughal Narayanasamy, and here I am coming with the title of Development on Scope of Aqueous-Based Energy Storage Devices. This is my first international faculty development program, which was hosted by Futuristic Research and Mechanical Engineering Department. First of all, I would thank our convener, Dr. G. Prabhakaran sir, and co-convener, Dr. V. Thanigevelan sir, and all the coordinators, Vetrivelan sir, Krishna, Mr. Krishna sir, and Ganesh sir. And okay, let's go upon with the title. And first, let me a short introduction about myself. As the Ganesh sir also told this about, I have done my bachelor's in mechanical engineering in 2012 to 16, and during my bachelor's degree, as well, Dr. V. Thanigevelan as a co-supervisor for me. It's a great privilege for me to attend seminar with him. And I have done my master's in nanoscience and technology in 2016 to 18 with the PhD in material science at 2018 to 21. Here I have shared my official mail ID and official contact details for in case of future research helps, it can be further helpful for research. And yeah, during my master's research area, I have been worked on 1D nanostructure material reinforced for nickel composite coating, which used for pulsed electrode deposition, which was funded by UGC DAE. And after that, during my research, during my doctoral research, I have been worked on development of vanadium-based nanohybrid cathode materials on zinc-ion batteries, which was funded by Jasmine Jiangsu Scholarship, which is a prestigious award provided in the Jiangsu province. Followed by, after completing my doctoral degree, I have been worked like 6 to 7 months as a research associate, worked on the fabrication of bimetallic sulfate-based energy storage devices, which was funded by DST project. And recently, I have joined as a postdoctoral researcher here in South Korea, working on electrochemically etched magazine-based anode materials for lithium-ion battery. Yeah, as Mr. Ganesh said, that these are the list of awards and honors. I have been awarded awarded several times with the China University competitions, and one of my article published in Journal of Material Research also been selected as best paper of the year. And I have now awarded first prize in Sino-Foreign Postgraduates Academic Forum conducted in Shanghai Jiaotong. Okay, let's get into the topic. Here I'm going to discuss about the development and future scope of aqueous-based energy storage devices. These are the topics I'm going to discuss about: introduction, major drawbacks of aqueous batteries, aim and future objective, main objectives, fabrication of aqueous battery, and some working demonstration of my previous works. And then we'll go for summary and outlook. As I mentioned here, the increase of lithium-ion battery market is increasing day by day. As of we seeing the North America compared to Europe, Asia and South America and the Middle East Asia, it's still getting a rapid increase in the global market. So the increase of lithium-ion battery is also getting increased, and the manufacturing of lithium-ion battery also a drawback for us, since it is of highly inflammable and highly costly. So we have to find an alternative solution for lithium-ion battery. So in such cases, what we introduce is that aqueous batteries. First, we'll see about the major some major introduction. Advances of cellular communication and personal mobility and evolution closely linked to energy storage devices, which attained tremendous success in the globalized battery sector. And also the demand for fossil energy increases day by day, and the importance of developing sanitary and sustainable energy sources and their economic production methods are increasing rapidly day by day. Particularly in this COVID era, the usage of aqueous batteries are more reliable when compared to the lithium-ion battery, because it is not an inflammable. It can be used in high thermal stability it can attain, and The recent research community of battery chemistry hugely focused on the development of various electrode materials for the metal ion batteries like magnesium, calcium, zinc, aluminum. Like that, there have been a variety of aqueous multivalent batteries. Particularly, even though magnesium, calcium, aluminum more are there, the battery chemistry focus mainly on zinc ion battery. Why? Because means when compared to all other aqueous batteries, it is giving an high energy density and high power density and giving a long cyclic life. In particular, the vanadium-based compounds have a bigger family with a different structure and chemical composition and electrochemical properties, which provide a huge possibility for the development of emerging electrochemical energy storage. Yeah, this is the timeline chart of the development of various aqueous batteries. As we can see here, the aqueous zinc ion battery is not a new era. It's already been developed in the 1986, but it's still under the research. Why it is still under the research means the usage of anode, which we use here in zinc ion batteries, is as common zinc sheet. So an alternative for this anode material and an alternative for this electrolyte is still complicated. So as per the current research, we are still using the zinc sheet as an our anode. And for electrolyte and commonly used ZnSO4, zinc sulfate. Why we are using zinc sulfate means it's giving a mild pH. So we are oftenly goes with the zinc sulfate electrolytes, and also the ionic conductivity is much more increased than that of the other aqueous electrolytes. So we are going for zinc based electrolytes. This is the specific capacity versus discharge potential of various cathode materials for zinc ion batteries. In zinc ion battery cathode materials, we can roughly say that the vanadium and manganese based material have the high tendency. Particularly, the vanadium based materials will provide a greater specific capacitance rather than the manganese based material. When the manganese based material give the potential of even they can rise to 2 voltage, but the same can be achieved in 1.5 voltage. The specific capacitance increase is more rapid and it is more reliable and consistent when compared to the manganese based material. Yeah. Here in figure A, we can see that the number of publications devoted to aqueous batteries till 2015, there have been no reports on the aqueous based batteries. But whereas in 2016, 17, 18, and 19, still a rapid involvement of zinc ion batteries when compared to same as lithium ion battery. In the market, when compared to lithium ion battery, zinc ion battery is also increasing in day by day. The major consequences in the zinc ion battery is that it is having more corrosion resistance, and for hydrogen evolution reaction, we will be using a mild acidic pH. For oxygen evolution reaction, we will be using an alkaline medium. That's the major thing we will be discussing about this thing. And for non-metal ion type, they are using a hydrogen ion and fluoride ion, maybe some other kinds of ion also be used. In metal type ions, the lithium, sodium, potassium next to the primary batteries. The secondary batteries like zinc ions, magnesium ion, calcium ions are now emerging. Yeah, as I earlier discussed that zinc ions, the zinc ions ionic conductivity is more higher than that of the lithium and sodium ion. So the usage of the molecular weight also consistent for zinc ion batteries. When we using the pure water as an electrolyte, it will be going beyond 1 to 1.3 voltage, whereas in salty electrolytes it will be going beyond 2 voltage. And we can these water and salt and water and bisalt can be used as an ionic liquid imidazolium based aqueous electrolytes. But whereas we will be preferring more about water and salt in a water and salt electrolytes. Particularly, these are the major advantages and disadvantages in aqueous electrolytes. What is the major advantages? It have an intrinsic safety and inconsumability, and it will give the high ionic conductivity. And the fabrication technique will also be not an time consuming. Since it is an aqueous electrolyte, we can be used this in an aqueous medium. We know we need not to be used in any other glow box facility. The only drawback in this is just it is only having a narrow electrochemical stability and relatively inferior capacity and limited working temperature range it will be attained. Whereas in organic solvent, it can go more beyond that 4 voltage, and it is highly protective to solid interface of ions and transportation of electrolytes in it. The major disadvantage is that it having an explosion and safety issues, and it may not have a good conductivity property. And in ionic liquid, extremely high voltage it can go about, and the low volatility and high thermal and electrochemical stability and high salt solubility. One of the major drawback commonly we can see all in this is it is reliability to performing in a low capability with a high viscous medium. It will go, but the majorly we will be focusing on aqueous electrolyte. Why? Because it is highly safety and low cost and more cheap when compared to the all other electrolytes. What are the major issues we will be finding in the aqueous electrolytes? Means the hydrogen evolution will be occurring on top of the anode passivation layer. It can tend to form and dendrites on it, and it can also lead to form corrosion on top of the anode medium. Whereas in cathode, the electrolyte will be having a dissolution problem. The ion transportation can be very slower when compared to the solid electrolyte interfaces, and this is an aqueous electrolyte, right? So we can also have evaporation problem. In that, the zinc sulfide can be separated as zinc partially and sulfide partially. And sulfide in getting at a high temperature, the sulfide passivation layer can be easily removed from the active layer. Yeah. So what we do is for preparation of cathode material, we will be firstly focusing on several techniques are there, but we will be focusing on hydrothermal, like co-precipitation, salvothermal, sol gel, spray pyrolysis, hydrothermal, magnetoisotropic solid state reduction, and many other simple procedures are there for electrode preparation. But what we focus is that hydrothermal and salvothermal using a simple autoclave method, which successfully demonstrate an eco-friendliness, low cost, demonstrated and high energy efficient, and it is a clean method. For doing this kind of research in a small lab with no facilities, we can directly go for hydrothermal or salvothermal, and it's a promising method for physicochemical characterization, and it provide an unique morphologies. Particularly when using hydrothermal and salvothermal, it will be giving a unique morphological property. Those unique morphology properties given better electrochemical performance for the ion transportation of oxidation and deoxidation. Okay. This is the growth of cathodes for zinc ion batteries. Here we can see in this time chart. As I said earlier, it was started in 1986 with they have tested with the MnO2 salts. With later on, they have tested with several manganese-based oxides. After 2017 to 18, they have also started with vanadium-based materials. Since it is having supersaturated multivalent state of vanadium, we are using that as a cathode material for zinc ion battery. Yeah, these are the major objectives we will be focusing on. We will be searching about we search about the earth abundant, low cost, highly efficient cathode material, and then we will be developing our electrode material using an hydrothermal material and understand its reaction parameters and influence product formation by adapting newer techniques. And then we will be discussing about the electrochemical performance of our prepared cathode material, and then we will be investigating the structural and chemical stabilities of the prepared vanadium-based nanohybrid cathodes. And the real motto of this project is to reduce the irreversible capacity loss, which was more in the lithium-ion battery when compared to the non-aqueous medium. We will be focusing here more on irreversible capacity loss of the nanohybrid cathode material. Finally, we develop the structure. We develop a firm understanding of structure, property, performance relationship of high discharge capacity of either manganese or vanadium-based nanohybrid cathode materials. Yeah, these the cathode material electrode type can be classified majorly on three types. One is of layered structure, tunnel structure, and nasicon structure. And the major advantage of in zinc ion battery is that the capacitance and the cyclic number, the rate capability was much higher when compared to the tunnel-like structure and nasicon-like structure. So what basically I suggest is that the layer structure of a metal oxide or transition metal dichalcogenates or bimetallic transition metal dichalcogenates, we can do with the variety of experiments of electrode materials basically on layered structure will give an better capacitance. So these are the fabrication techniques of the aqueous based battery: the negative case, spring, spacer, and the zinc sheet, which act as an anode, and a separator, particularly as a polymer based separator we will be using. And in working electrode, we will be using carbon sheet as our substrate, and on top of the carbon substrate we will be coating our cathode material in the ratio of 7:2:1. For example, say our cathode material have an active material 7%. We supposed to use 2% of carbon black and PVDF, including NMP solution, so that we will be getting rheological ink-like solution we will be prepared. And after applying using Dr. Blade's technique, it can be easily coated to carbon substrate. And after capping this coin cell type, we will be having a complete setup of zinc ion battery. Here I can say as a demonstration, we'll be having a zinc sheet and our cathode material, the ZnSO4 as a common aqueous electrolyte we will be using. In that, the Zn2+ ion insertion excitation electrochemistry will improve the better electrochemical performance when compared to the any other non-aqueous medium. Yeah, these are the short summary of the research findings we have found. We will be doing with the hydrothermal or solvothermal method. With the in situ grow or self-assembly, we will prepare the electrode material. For physical characterization, we'll go like XRD, Raman, XPS, and TGA. Morphological characterizations like FSM, TEM. And finally, we will be studying the electrochemical property of our material, which we prepared, like some hybrid of oxides and carbides or graphene oxide hybrid with selenium. Here I have two of my previously published works to discuss shortly about it. And this is of morphologically retained growth of V2O5 by oxidation of V-mexines acted as a cathode material for zinc ion battery. It was published in Chemical Communication in the year of 2020. Here we can see that I used a vanadium aluminum carbide V2C as a mexine, and I have directly used my V2C mexine in hydrothermal heat treatment. At various degrees centigrade of hydrothermal heat treatment, I found that at 160 degrees centigrade, the formation of V2O5 is not incomplete. It's still incomplete, and in V180 it is still consistent, and growth of crystalline V2O5, it's an external surface acted as an existence of stacked layers still pertains, and whereas in V200 the mexine was fully aggregated and V2 has been fully disappeared from the stacked layers of V2C. The existence of various morphologies demonstrate this. Mexines can be used as a facile precursor for creating tailored unique morphologies. When coming to the Raman spectra of vanadium carbide, which is of different high heat temperatures. In vanadium 180, I found out that the presence of V2C and also vanadium 180 is partially present in it, whereas in V200, the Raman spectra is fully like an V2O5. whereas in V2C, and V160, it's still the same as V2C. So I found out that V180 have the partially oxidized V2O5 present on V2C. Uh, I have taken XPS for my material. It shows in XPS analysis we find the chemical structure and valence state of V2C. V2C at V2O5 we will be finding, and I found out that it is of multi-oxidation state with the V2O5 and V5 plus state and V4 plus state also present. So this multi-oxidation state leads to the better electrochemical performance. What I have done is I have done the CV curve for V160, 180, and 200. I noticed that the slope and plateau for V180 is much better when compared to that of the V180 and V200. In V160, what happened is that the V2O5 is still not present, so it depletes the V2C structure, whereas in V200 degrees centigrade, the V2O5 suppresses the V2C performance. So finally, I noticed that V180 will give the better performance also using CV curve. Given a pair of oxidation and reduction peaks were found, and which is highly pertains for zinc ion battery performance, reversible and irreversible capacitance retenuation. For this material, I have also done galvanostatic charge discharge cycles. I noticed that even though the V160 degrees centigrade giving a good rate capability, but the specific capacitance was low when compared to V180. But in V200, the rate capability was still not the stable, and in long cycling performance, it achieves an good rate capability of 89% with the Coulombic efficiency of around 98%. In Nyquist plots, also we found that V180 degrees centigrade gives a lower charge transfer resistance when compared to the other. What are the key findings we noticed is that the V2O5 nanorod formed embedded extremely internally on the surface layer structure provides enough electroactive surface for intercalation and deintercalation, and the partially grown V2O5 nanorods and carbon defects in its edges ensuring high rate capability, and it also inhibits the structural recombination even after long cycling performance. And in the other hand, the introduction of oxygen vacancy of could speed up the advantages of zinc ion migration and the proliferation. And this was the first partially oxidized magazine article published in Chemical Communication. Here in the next work, we will be in this work we will be discussing about vanadium diselenide hybrid with graphene oxide. What we have done is we have took a graphene oxide precursor and vanadium precursor. We have given a heat treatment. After heat treatment, I noticed that marigold-like structure was formed with using reduced graphene oxide as a template, acted as a template, gives a better performance when compared to the pure VAC2. Here in Raman spectra, we can also see that D band and G band, which is more consistent for graphene material, was present in the VAC2 material. With that, I confirm that the chemical composition of reduced graphene oxide and VAC2 was tightly bonded to each other in the structural composition. In XPS findings, we found that the vanadium with the mixed valence state is beneficial for zinc ion. So also we have tried with the oxidation state of V3 state and V4 state. It's giving a better performance when compared to the V5 state. So also in the CV curve, we can notice that the hybrid material giving a more current and the increased potential ratio when compared to the pure VAC2. We further done the experiment with the different varying current densities, like 5 millivoltage, 2 millivoltage, Like that we have varied, and the comparison of charge galvanostatic discharge profile clearly says that the hybrid of graphene with shows then better electrochemical performance when compared to the pure. The rate capability was also more stable when compared to the pure VAC2. Even the cycling performance giving a 97% of capacitance retenuation, and which is highly preferred for confined strong penetration of ions in it. So the key in the as well in the key findings, we found out that the confined strong penetration of BSC2 nanosheets giving an outstanding rate performance. With the vertically confined marigold structure, it still inhibits the structural degradation, and it also helps the electron transport pathway for further diffusion pathway. These are the four major things to be concerned when we are focusing on zinc ion battery. First, the future work should be focused on in situ characterization to further deeply study about the in-depth mechanism of ion transportation in it. Precise that the current voltage and time and cycling number should be more stabilized when compared to the previous literature's work, and then unified activation and the activation of mechanism using hydrogen ion transportation, and or else the some other metal ion doping or dissolution of ion. The intercalation and deintercalation chemistry should be much more deeply studied, and also the activation of ions is also more important, and it plays a key role in activating the cathode material, because the substrate we are using is carbon. When activating with the aqueous electrolyte, it can tend to an good rate performance, and by using a better surface area property material, it given good impact in the electrochemical energy performances. These are the summary and outlook to be discussed in the interface engineering of zinc ion battery. Majorly, it will be focusing on one will be on electrolyte interface, and the other on anode electrolyte interface, and from cathode electrolyte interface. Particularly in zinc ion battery, the drawback is zinc dendrite growth for large scale energy storage devices, which need to be steadily understanding the property for more number of cycles. Some newer strategies like surface modification, like artificial solid electrolyte interface, physical coating or chemical decoration, electrolyte optimization, or with the additive gel or organic solid electrolytes, alloying the material with some other material, being widely applied in the zinc anode or electrolyte interface, in order to deeply investigate interface and solve the problem regarding zinc anode, and understanding with the interfacial chemistry like zinc deposition behavior, and some we can alter with some electrodeposition on top layer of the zinc sheet can be also done to increase the racial design of anode electrolyte interface. Thus, the studies of stable interface and zinc dendrite suppression and promising direction to optimize several vanadium-based bimetallic transition metal dichalcogenics. Yeah, that's all. That's all about my presentation. Thanks for watching. Is there any more questions from this?
Participants, you can go for now. If you have any queries, you can discuss with our chief guest. Participants?
Good afternoon, sir. I'm audible?
Yes, sir. Yes, sir. Please raise your question.
Yes, sir. Sir, very well explained by Dr. So basically my question is that we are moving towards electrical vehicles, sir.
We are
Hello,
moving
I'm,
towards the.
I'm audible?
Yes,
As
sir.
we are moving towards electrical vehicles, sir. So, are you
Yes,
getting me,
yes.
sir?
Yeah, I'm audible, sir.
Yeah, I'm not audible.
Sir,
Hello.
you are audible, and your question is also been you are moving towards electrical vehicle, right?
Yeah.
Yes,
We
sir.
are moving towards electrical vehicles. So the basic now in future we will face the problem of dispose of the batteries.
Yes,
because
sir.
we are going to use a lead acid battery as well as lithium-ion batteries. So
Yes,
in
sir.
your yeah. So what do you think? How we can dispose of, or how we can linger on the life of the battery so that we need less to dispose of, instead of dispose of we can reuse it. Is it
Yeah, in
so?
that case, yeah, for that major reason only we have been moved to the aqueous batteries. Why? Because means the disposal of lithium ions is highly costly and it is more
Yes,
toxic
sir.
when compared to the aqueous batteries. And these
Yes,
aqueous
sir.
batteries are more eco-friendly. And in the recent days, we also noticed that the
Okay.
lithium battery
Uh,
was highly inflammable. So we can shift over to the
yes, sir.
aqueous
Highly
kinds of,
inflammable.
yeah. But the major drawback in this kind of aqueous batteries is that it cannot provide the much higher voltage when compared to the lithium battery. So what we use
Ah,
is that we increase the quantity of active material, and we increase the electrolyte medium, and by tuning with some uh, ionic solvents, we can still improve the aqueous battery technologies.
okay,
It
sir.
was,
Okay.
yeah.
जी, ठीक है. That's, thank you, sir.
Thank you
Very
so
much.
much, sir.
So, but we one thing more, sir. Hello.
Yeah, yes, sir.
Yeah, if we compare the costing, because as in India, like country like India, every person is approaching towards the economical thing. No? Either you take the electrical vehicle, something like that. Let's say I take an example of this your simple scooter, electric vehicle,
Yeah,
which is lithium-ion battery, that is 15,000 costlier than the lead-acid battery. So, what
yeah.
is the cost if you are studying of this aqua acid batteries? So, what is the
Particularly,
cost for that?
particularly, I tell with the example in China. In China, the commercial use of aqueous batteries have been arrived in the year of 2020 itself. For example, if you purchase an e-vehicle, it will be cost around, in Indian money, I'm saying, it will be cost around 30,000 or 40,000 when we purchase lithium-ion battery. When we purchase an aqueous polymer batteries, it will be only around 7 to 8,000 in Indian money. The usage of aqueous batteries are more, and it's still in the commercial in China. Maybe in future, in 1 or 2 years, it will be obviously arrived in India. If it is arrived the Indian market, I'm sure that we can see the down of lithium-ion battery costs. So only the solid state lithium-ion batteries are more using here, and in India also some polymer kind of lithium batteries are commercializing in India to reduce the cost of batteries.
Hello, sir.
Yes, sir.
Uh, Good morning, sir. Thank you for your nice presentation. It's very clear, and you address the main issue, like the recent trend in the research.
Yes, sir.
I just want to get some clarity on a few points, like how we can implement this kind of technology in India, because this is the trend with all the developed countries. They are looking into the electrification because they have sufficient power, sufficient electricity, and all. So they can go for this kind of electrification in the vehicle and other things, because their
Yes,
population is limited and their facilities are very well organized.
yes.
How we can bring this kind of electric vehicle or battery technologies to India, and how it is possible, sir? Do you have any recommendation for that?
Particularly in telling about the consequences in India, even for testing the electrochemical performance, particularly I say about my PhD experience. My partial work of my PhD done in China and some part of the work done in India. For doing some electrochemical experiments, here it takes not a much time, and it's not a time consuming. But in the case of India, we are still lack of instrumentation techniques. We are still in lack of instruments, and the purchasing of instruments are also from the European countries. So we are still in the developing stage. For example, I have done my partial research in CSIR SICRI. There we haven't more enough facility, and even though they are using aqueous kinds of battery in the real-time application inside their campus atmosphere, you can see. I suggest is that the fabrication of battery testers should be done in India. We must manufacture that electrochemical instrumentation. All the instrumentation have been done, and after we fabricate for ourselves, we can directly use them in real-time application. As of now, we are depending some other countries for exporting.
Okay, sir. Thank you for the clarity. And one more request. So what is your recommendation for future research in batteries? Like if you want to recommend some idea for future researchers in battery technologies, what kind of technology or what kind of issue you will ask them to do?
I suggest that particularly in India, we are in lack of electrochemical workstation. We are in lack of lab facilities. So I preferably say that going with the lithium-ion batteries or some other batteries will be not an eco-friendly environment, because we need to buy an glow box facility, and the experiment also need to be done in inert gas atmosphere. Those kind of many circumstances are there. But if we move for aqueous-based battery, we can directly fabricate the battery in the room temperature itself, and those electrochemical workstation will also not and much costly. I believe that for smaller labs, like initial startup laboratories also can be more reliable to work on aqueous batteries. I believe that I strongly believe that the zinc-ion battery technology will be an outstanding technology in near future, up next to the lithium-ion battery.
Thank you, sir. Thank you so much.
Thank you so much.
So now I call upon our one of coordinator, Mr. Krishna, for vote of thanks.
So my voice is audible, sir?
Yes, sir. We can hear you, sir.
Sir, so regarding this electro plates, sir, in batteries, is there any new technology for conductivity? Is there any new technologies? Sir?
What kind of conductivity you are telling about, sir?
So
You are asking about the
for example,
deposition.
Yeah, no, sir. That electro plate itself, if you change some material, so like that, any new inventions are going to?
Here, what we are using is silver nitrate paste and some copper tapes. Commonly, for a small startup companies or startup adventure, I will say that copper tapes we can prefer. Preferably, I suggest it's good ionic resistivity and good conductivity also we get. So I suggest with the copper tapes will be much better. In case if you need if you want like a paste like material, you can go like a silver chloride, AgCl paste you can use.
So it is right time to go for a vote of thanks. Mr. Krishna, I request you to give for a vote of thanks.
Thank you so much. Do you have any questions? After I go for the formal. Participants? So anyone having any more questions, sir? Or I can go for the formal vote of thanks. Thank you. Good evening to all present here for this International Faculty Development Program on Futuristic Research in Mechanical Engineering. On behalf of the Department of Mechanical Engineering, Institute of Science and Technology, Ramapuram, I'm very much glad to have this opportunity to thank you all at this International Faculty Development Program. First of all, I'm very much thank our resource person of the session, Dr. Mugilan Narayanaswamy, for giving an excellent presentation on this energy storage. It was wonderful, sir, to knowing about the batteries, where we are, what we are going to do. Thank you, sir. Thank you for the much more information. Thank you, sir.
Thank you, sir.
And I take this opportunity to thank our honorable chairman, co-chairman, respected director, respected dean, ENT, respected vice principal academics, and vice principal. And I am thanking our beloved HOD for giving this opportunity for us to conduct this session. Finally, I'm taking this opportunity to thank all the participants from the various colleges. I believe session is very good. Thank you. Last but not least, I take this opportunity to thank the coordinator and the organization for this. Thank you, one more. Thank you.
Thank you so much, sir.
Again, sir, thank you.
Thank you, sir.
I know that you are in how much busy schedule, and in spite of busy schedule, you accepted our invitation and you allotted for us this much of time for presentation. It was really very nice and wonderful. The information
Thank you, sir.
can be gathered by the participants, and it may be or it must be useful for them in the future research.
I hope
Thank
it
you,
will.
sir.
Thank you,
sir.
sir.
Thank you. Thank you. So participants, please fill the feedback. It's mandatory to secure your attendance.